Welcome everyone to this Create webinar. Today we'll be learning about a new resource to understand advanced lighting controls, information brought to us by Scott Shooter, Principal Engineer at Slipstream. And Gabby, if you got that next slide for me, please. Thank you. Information about this webinar, future webinars, and about resources from the Create Energy Center are available at createenergy.org online anytime. Check out many resources there. We actually have 3 upcoming webinars that I think are on our next slide. We have an architectural design webinar coming from Jason Oliver from College of the Canyons. We have a heat pump resources also with Slipstream, Scott's organization. And then considerations for colleges installing electric vehicle charging stations. I think some lessons learned and experiences from Ken Walls and Kevin Cooper. And so all 3 of those coming this fall, but dates yet to be determined. So watch createenergy.org and watch for email bulletins with information about that. 2 coffee hours coming up soon. We have September 22nd, using drones for energy courses. Ed Franklin, who I think is right here on this call this morning, and EV chargers on campus. Also Ken Walls and Kevin Cooper, related to that fall webinar that's coming up. So lots of information, createenergy.org, and you can always reach out to Gabby Temple with questions. Gabby's email address is there at the bottom. I think we'll turn over to today's presentation. Today's presentation will be from Scott Shooter. I will tell you some official information about Scott. So Scott is a principal engineer at Slipstream with 15 years of experience leading research projects that focus on emerging technology performance in the built environment. His commercial billing experiences encompasses field measurement and modeling of emerging technology performance for energy efficiency, electrification, load shift, load shed, and continuous demand management. Scott manages projects, designs experiments, and conducts both theoretical and field research to analyze the applicability of new technologies to federal and state agencies and utility programs. I'm very glad personally to see this presentation from Scott. I've known Scott for quite a while. We met a long time ago at the University of Wisconsin when we were both in graduate school, and he has generously over time helped with some building energy modeling resources for my high school physics classrooms. So I'm really grateful for that. Scott's done great work in this field for many years. I'm especially excited to see this talk as we've recently done work in energy modeling. There are so many tools like task tuning for lighting, for example, that for small investments can make great energy returns in buildings. So I'm really excited to see what we'll see with advanced lighting controls today. And with that, I'll turn everything over to Scott.
Thank you, Jim. It's great to see you. Appreciate that introduction, and it's great to be here. I am sharing my screen, and I hope you can see my slides. Is that true?
Yes.
Okay, great. So yes, I'm Scott Shooter. I'm a principal engineer with Slipstream, and today I'm going to be discussing a resource that hopefully will be useful for you all, whether in your professional career or your classes, that is tailored to advanced lighting controls. So we'll be starting with an overview of advanced lighting controls and the kind of project that developed this resource, and then I'll go into more details about the different training modules and topics that are covered. And then I'll cover 2 of those topics, task tuning, which is what Jim alluded to a second ago, and the integration of lighting controls and HVAC controls. And then I believe there'll be some time at the end for questions that I'll hope to address. So what problem are we trying to solve? Advanced lighting controls have been around for a while. It's a mature technology, and they've been shown through numerous projects to save significant energy. Kind of depends on the type of space you're putting them in, but 20% is about right on average for additional lighting savings beyond an LED only retrofit. And us and some of our project partners had worked with the Department of Defense to demonstrate that type of savings in multiple Department of Defense facilities, and found through doing that not only is there a bunch of energy savings, but that there's a pretty big knowledge gap in the from the people that could be implementing these types of controls in their facilities and in their buildings. So we set out to address that gap by developing this kind of comprehensive education and training curriculum. And then once it was developed, kind of the tail end of the project is now, which is we're trying to disseminate those resources to a broad audience just to get people aware of the videos and the trainings and start to understand more about advanced lighting controls. I'll go through this pretty quick, but just give you a sense of the project. We started out in task 1 with planning the trainings, and that mostly involved interviews of stakeholders like energy managers, designers, contractors, really to understand where they were at, what their decision points were, and what the barriers and opportunities they perceived are for advanced lighting controls. Once we understood those, we set about developing our curriculum. In task 2, we developed a kind of high-level set of videos covering multiple different topics. Those high-level, kind of shorter videos were more aimed at installation energy managers or non-technical audiences. And then in task 3, we expanded on those trainings and topics into going into much more depth for a more technical audience like designers and operators. And we're kind of in task 4 right now where we're disseminating these resources to a broad audience. So yeah, what did we develop? For that more non-technical audience, we covered 6 different modules. We started with case studies of advanced lighting controls showing how these technologies could have been successfully implemented in real projects. Then we talked about the fundamentals of lighting controls, some common advanced control strategies, and various types of controls. Then we gave an overview of the Design Lights Consortium, which is a great resource covering a lot of advanced lighting controls and lighting topics. And finally, cybersecurity is becoming increasingly important, and it's definitely important for a Department of Defense audience, so we covered that as well. Under each of these modules, there's 16 total topics. Those videos cover range between 10 and 20 minutes in duration. Here's a list, I guess. There's 4 demonstration examples, field demonstration examples. There's fundamentals covering the basics, code requirements, and a subset of advanced lighting controls called luminaire level lighting controls. And then we talk about strategies such as task tuning, daylighting controls, occupancy and vacancy, and HVAC integration. And then we talk about the difference between wired and wireless controls, standalone and network controls, and how to estimate lighting control savings in your buildings. And then I mentioned the Design Lights Consortium and cybersecurity topics as well. In the more technical, longer duration videos, we covered each of those same topics in more depth, ranging from 20 to 60-minute long videos. And for those of you interested in continuing education credits, those are available for these videos. And we covered the same topics with the addition of a couple of topics that focus on emergency lighting and their associated controls. And then I put these links in the chat and just wanted to emphasize that all those videos are now available in at a couple different places at no cost for viewers. So check them out. And then, yeah, during the rest of the presentation, I was going to cover 2 of the topics at a pretty high level. And the first is task tuning. So I'll begin this section by describing what task tuning is as a control strategy and the importance of incorporating occupant feedback, and then segue into a discussion of task tuning opportunities and the potential for task tuning savings in a sample set of space types, and conclude by identifying some best practices for integrating task tuning into the design or redesign process. Task tuning is a setting within a fixture's maximum light output to something less than 100%. So it's often in response to a space that would otherwise be overlit, or as a means to reduce glare. It's sometimes referred to as institutional tuning or high-end trim, but I'll just call it task tuning because it's a little simpler. Task tuning is a way to both capture additional energy savings and optimize light levels to improve lighting quality. This control strategy utilizes the inherent dimmability of LEDs to reduce average light levels in spaces in order to bring them into alignment with recommended values. So recommended average light levels are based on what's going on in the space. For example, you don't need the same amount of light for someone reading very fine print as someone working on a computer or someone watching a presentation. However, we found that this amount of light in a space is often much higher than is necessary. So tailoring the light level to match the specific needs of a space is an advanced lighting control strategy and part of the next frontier of lighting energy savings. It does require the ability to dim the lights. However, with more and more dimmable lighting in the form of LEDs in spaces, the potential for task tuning is growing. So how does task tuning save energy? Here we see a light level provided by an ideal lighting system as a function of its power. As you can see, as the lighting power increases, so does the amount of light in the space. For this idealized, untuned lighting system, you would measure 50-foot candles of electric lighting, which is a measure of light level or illuminance, when the system is providing 500 watts of electricity. That's at its maximum power. For this example, the recommended light level via the Illuminating Engineering Society is 40-foot candles. So as we tune the light levels down to this recommended level, that results in a power reduction of 100 watts to 400 watts. That was instantaneous power savings. But how does that play in terms of energy savings? So here's a plot of the same idealized space over a typical day. Note that this system does not have daylighting or occupancy controls. So in the morning, lights come on to their full power and remain there throughout the day. And then they're shut off at night when the last person leaves. After tuning, the lights still come on at the same time. However, they now come on to their tuned power instead of their full power. The difference in power savings summed over time is the energy savings. An important consideration when implementing task tuning is occupant comfort. Because task tuning is essentially a trade-off between energy consumption and light levels, it's important to balance energy savings with occupant visual comfort. Light level reductions that are too aggressive may result in high energy savings, but at the expense of occupant satisfaction. Complicating this balance is the fact that occupants perceive light levels differently, both between individuals and for the same individual under varying situations. Because of this complication, we recommend incorporating occupant feedback into the task tuning process. This strikes the balance between energy savings and occupant visual comfort. Although this may result in lower immediate energy savings, it's likely to increase energy savings persistence, as facility managers will be less likely to override tuned controls because of occupant complaints. And anecdotally, you may be surprised to receive feedback that an even lower light level than the recommended level is actually preferred. That's been the case in several of our field demonstrations. To quantify the magnitude of potential energy savings and light level optimization, I'll refer to some of Slipstream's previous research in which we characterized the light levels in a sample of spaces in Minnesota. This characterization included site visits to accurately measure light levels in these spaces that LED retrofits had already occurred. We compared measured light levels, also known as illuminance levels, with the industry recommendations as defined by the Illuminating Engineering Society, or IES. It's important to note that these recommendations are in line with the Department of Defense requirements, which are less applicable for this group, but very applicable for our target audience as part of the project. Summarized here in this table are the mean measured illuminances we found, the IES recommended illuminances, and the task tuning percentage. which is the maximum lighting power limit in a task tuning scenario. Note that implementing the task tuning percentage would bring the actual and recommended light levels into alignment. You'll note that for all space types, the mean measure luminance was higher than the IES recommendation, indicating in several instances significant opportunity to both capture energy savings and improve lighting quality by minimizing the potential for glare from overlit spaces. It's possible to incorporate task tuning into the design or redesign process during a lighting retrofit. Lighting practitioners regularly use photometric analysis, which is completed with computer modeling software to estimate light levels or expected illuminance values based on a specific fixture and the layout of the fixtures within spaces. This image is an example of a point-by-point photometric calculation. Overall, photometric analysis does a good job of estimating light levels and is quicker than field measurements since it does not involve lengthy site visits. And since it's already a part of many projects, service providers could rapidly deploy it for quick determination of light levels and the corresponding task tuning set points. Additionally, Department of Defense projects require the completion of this analysis to confirm the light levels are consistent with its requirements. Photometrics are often offered as a free service by manufacturers, distributors, or lighting sales representatives. Contractors can readily access this no-cost resource, and design teams typically employ staff not only capable of performing it, but that regularly utilize photometric analysis as a part of their typical design. The same computer modeling software used to generate point-by-point photometric analysis also summarizes those results in a tabular fashion like this table. These tabular results describe various parameters that guide lighting design decisions, and they always include the estimated average illuminance, or light level, which is a useful tool for identifying opportunities to optimize light levels via task tuning and capture the associated energy savings. Like if the average illuminance is predicted to be higher than what's necessary, there are savings opportunities there. This is an example of a control matrix that was created to illustrate documentation of lighting control design intent, which encourages the completion of photometric analysis during a project's design phase. This type of documentation is not standard practice for many retrofits, so it must be requested by the project manager of the retrofit or new construction project. In this example, the task tuning percentage is identified in the column on the far right. Again, that'd be the maximum lighting power limit. In a separate DoD, Department of Defense demonstration, which is the topic of a whole nother video, we found the implementation of task tuning to be most successful when implemented using this matrix. Alternately, light levels can be measured and adjusted during installation and setup, but that approach was found to be more time intensive, and the implementation itself did not be a priority for the personnel involved in configuring the lighting system. A control matrix or schedule such as this, which details the lighting control design intent, can be easily incorporated into design documents, which ensures that the contractor has a clearly defined scope that must be implemented during the construction phase. However, as mentioned previously, care should be taken when implementing task tuning to understand user needs of a given space, so these percentages should be a starting point and adjusted as needed through occupant feedback. If field measurement is needed to confirm target illuminance values have been achieved or to investigate existing light levels prior to a retrofit, there are some best practices to keep in mind. The light meter should be placed on the work plane or held away from your body so that you do not cast a shadow on the sensor. It's best to record measurements at a location where tasks will be performed and not in the corners of a space or directly below a light fixture. It's also important to capture the contribution from electric lighting only, which don't include contributions from available daylight in the space. This can be done by either recording measurements after dark or by recording the difference between measurements taken both with lights on and with lights off. Any uncertainty in this measurement can be minimized by pulling down any blinds that are available in the space. Once you have the lights on and lights off measurements, you take the difference of those to capture the electric lighting portion of the light levels. That's the conclusion of the task tuning section of the presentation. More information on this topic is available on Slipstream's website and the Design Lights Consortium website. And note that the Design Lights Consortium maintains a qualified products list of network lighting controls and luminaire lighting control products that are capable of task tuning, as well as other advanced lighting control strategies. So segueing into covering the topic of HVAC integration. We'll begin by discussing what is HVAC integration, then discuss best practices and future trends, and conclude with an example of a Department of Energy project that integrated these controls in 5 commercial buildings. Lighting and HVAC together account for more than 50% of commercial building energy consumption. To obtain maximum energy efficiency, lights should be dimmed and HVAC set points should be adjusted whenever a space is not being used. Today, we're more focused not on an unoccupied period overnight, but on short unoccupied periods during the day. Since lighting is everywhere, luminaire level controls in the lighting can be leveraged to not only dim the lights, but also control the HVAC temperature set points when occupants leave the room. Integrating lighting and HVAC also gives a facility visibility and the ability to control the 2 largest energy consumers. So essentially, we're taking all the occupancy data that the lighting system is collecting and using it to more optimally control the HVAC. It's not uncommon today for a building to have multiple control systems, both for lighting and HVAC, and sometimes even multiple systems for each. In its simplest form, the integration of lighting and HVAC provides the ability to control lighting and HVAC from shared occupancy sensors. With a single point of control for both systems, shared schedules can be implemented, providing synchronized behavior of the light and temperature levels based on predetermined scenes as well as occupancy status. Energy usage for both systems can be aggregated and analyzed from one convenient dashboard, and energy conservation decisions can be made for both systems concurrently. This ensures maximum user comfort and safety. For example, in the case of a demand response situation, light levels can be dimmed along with raising HVAC temperature set points for cooling. This can minimize the discomfort that can occur when only HVAC is considered with very little effect on light performance. Integrated controls is the last step in a progression of energy conservation measures that can be implemented with lighting and lighting controlled upgrades. The first step would be to install quality, energy efficient LED lighting with the capability for control. Next is the incorporation of advanced lighting control strategies, such as task tuning, which we just covered, as well as daylighting and occupancy sensor. All of these are covered in other lighting modules and videos. These energy savings are available with network lighting. And once the lighting is networked, savings can also be extended to HVAC systems. Finally, to achieve the deepest energy savings, this network lighting system can communicate digitally with building automation systems via the BACnet protocol to allow for a broad variety of HVAC efficiency measures. Thermostat setbacks are the most utilized strategy for HVAC systems. When the occupant signals from the lighting system indicate an unoccupied status during the day, the active heating cooling set points are set back by typically a few degrees. In the case of a variable air volume system, additional strategies can be incorporated, such as in ASHRAE Guideline 36 to control the airflow. VAV box turndown or shutoff will reduce or shut down airflow when an unoccupied signal persists for 5 minutes. Similarly, the air handling unit supply fan can be set to minimum speed or shut down altogether in the case of an unanticipated unoccupied status. Ventilation can also be reset via demand control ventilation to allow for the recalculation of required fresh air via ASHRATE 62.1 and control of the outside air damper position based on the number of zones that are unoccupied. Oops. Yes. The benefits of integrating the lighting and HVAC systems extend beyond deep energy savings. Current control of buildings can be cumbersome with multiple lighting and building automation systems, each operating with their own control platform. Integrating these systems enables analysis and control from one user interface. Failure conditions can be easily assessed remotely from a central office or even from a facility manager's mobile device. This single interface can also allow for the intelligent analysis of energy usage over time and ultimately result in better decisions regarding space utilization. Since lighting and HVAC account for the majority of buildings' energy, integrating the two systems provides for sensible energy control, especially in the case of a demand response request. With integrated systems, we're able to combine a reduction in light levels with a reduction in heating or cooling taken by the HVAC system to maximize the comfort of the occupants while achieving the desired energy reduction. And finally, once a networked and integrated system is designed and installed, it can easily be scaled to incorporate additional lighting systems such as plug loads or window shades. These systems can adapt to changes in building use and can be revamped without costly rewiring with a relatively simple rezoning activity. HVAC integration can be challenging and needs a lot of thought put into it. The following slides provide a few best practices that will help with these challenges. HVAC integration projects require several individuals to divide ownership of a large number of tasks. This division of labor requires some forethought. This figure describes team member roles that are necessary for successful implementation. One individual, such as the electrical contractor, can actually cover multiple roles. The integration manager role is critical and should not be overlooked. Successful integration of different building systems will entail some challenges, and someone will need to be accountable for problem solving and team coordination. The integration manager could be capable of performing the programming tasks necessary to tie systems together, but regardless needs to oversee and coordinate the programming work done by other members of the team. The integration manager role could be fulfilled by the facilities manager, an energy consultant, a lighting professional, or any of the other roles identified here. The important thing is to make sure someone is accountable for this coordination. The typical HVAC integration project proceeds through planning, design, and then construction phases. In the planning phase, an economic assessment helps determine the viability of the project by comparing it against alternatives. For HVAC integration projects, a life cycle cost analysis may be a better representation of the project's value, as opposed to a simple payback analysis. A preliminary planning exercise can reduce challenges later in the process. Planning should include ensuring compatibility for systems integration and evaluating existing controls. Cybersecurity, which is covered in a different video, is definitely an important part of any HVAC integration project. Bringing the facility's IT staff into the project team early will mitigate issues that could be seen down the road. The design phase of the project includes elements surrounding lighting controls, network design, and HVAC control integration. The control phase includes the installation and configuration of these controls. The network is set up and the HVAC controls are programmed. Finally, facility operators and occupants are trained on the functionality of the new system. In the lighting and control design step, attention should be paid to the coordination of the HVAC and lighting zones. HVAC zones are largely driven by existing HVAC system design and thermostat or terminal unit locations. lighting control zones are usually based on luminaire and lighting control locations, as well as space usage needs. The coordination goal is to align lighting zones with existing HVAC control zones as best as possible. Zone matching does not have to be one-to-one. Multiple lighting control zones within a single larger HVAC zone would certainly be common in many instances. Within the design phase, some additional effort is needed to plan networking components and configuration. Whether the majority of the lighting control system is wired or wireless, some wired networking will be necessary for the integration. The electrical contractor takes the lead on this with help from the manufacturer's sales representative. The networks can be very simple, but some forethought is still needed. Considerations include how many networks are needed, the creation of a network diagram for documentation purposes, and whether the system will connect to a local IT network. During integration, facility IT staff, the lighting control commissioning technician, and the HVAC control contractor will need to work together closely to discuss and resolve network integration issues. Once the HVAC system is receiving the appropriate BACnet objects representing zone occupancy, the HVAC technician should be able to revise existing sequences to reflect the design intent. After the custom HVAC control programming is implemented, commissioning will ensure the system is operating correctly. HVAC integration is currently a complicated process, but manufacturers and integrators are making strides in simplifying every step. However, the upfront investment remains challenging. HVAC integration is most easily justified on large buildings with variable occupancy at this time. Capturing additional non-energy benefits will improve economics through value stacking. I previously alluded to asset tracking and space utilization, but additional value can be gained through future integrations with other systems such as security. Finally, participating in utility demand response programs can bring in additional revenue. On a recent Department of Energy funded project, Slipstream worked with key partners to successfully demonstrate HVAC integration of the Cree SmartCast lighting system. The objective of the project were to inspire the retrofit market to go beyond simple lighting fixture replacement. A part of this was to demonstrate the energy savings and barriers at each site. Excel Energy then designed a utility program as part of the overall project. This effort helped market actors get further up the learning curve, which supports broader adoption. The 5 sites were all in the Twin Cities area and included office, education, mixed use, vehicle service, and outpatient clinic areas. The HVAC systems that were integrated include variable air volume systems with hot water and chilled water plants, a dual duct constant air volume system, and packaged rooftop units. Integration was successful and saved energy at the 3 VAV sites. The average electricity savings across these sites was 3.8 kilowatt hours per square foot. Natural gas savings averaged 5.6 kBTUs per square foot. And applying the electric rates at these sites to the energy savings resulted in utility bill reductions of 45 cents per square foot. Simple paybacks were calculated using capital costs and utility incentives and averaged approximately 7 years. The sites with single-zone rooftop units had negligible savings due to poor zoning, and integration was not completed at the 5th site. Slipstream has produced several resources to help practitioners implement HVAC integration projects. One is an implementation guide, which goes into more depth on many of the topics discussed in this module. Another is a savings estimator that gives reasonable project-specific energy savings and economic estimates. Both of these are available for free to viewers like you. That concludes my presentation for today, and I'm happy to address any questions you may have. Again, just a reminder that links to the videos are all available in the chat, and I can provide additional links to other resources if you'd like. Thanks so much.
Scott, thank you for that presentation. There's really a lot going on there, and I like that you picked the two different subtopics that you did. We'll wait for some questions to populate in the chat. But while we're waiting, I actually have a question I'd like to start us off with, if that's okay.
Mhm.
So with task tuning of lighting, you'll change the power density in the space that's receiving that lighting. And so that, even before you do HVAC integration, may lead to lower cooling requirements or perhaps higher heating requirements. This used to be a lot more true with lighting that was a lot more power intensive than what LED lights are now. Is that
Yeah.
still a significant factor, or do we really, with LED lights, when we do task tuning, is it really just not enough power change in the space that you really see any sort of impact on the HVAC performance?
Yeah, I think you got it right, Jim. There will be an impact on the heating and cooling loads from task tuning. Um, Lighting with LEDs is already, 50% more, 50% less power and less heat than typical fluorescent space. 10% of that, or 10 to 20% of that, say that lower lighting isn't going to be that much, but you will see a little bit of cooling savings and a little bit of heating increase. Yeah.
Yeah, got it. Got
In
it.
a
Thank you.
climate like ours, in a in a building types like this, I think you'd see a small single digit percentage savings on HVAC.
Got it. So small. Yeah. Thank you. Thank you. There's a comment in the chat from someone that maybe joined after you posted the link to resources. Wondering if you could repost those.
Oh yeah.
Thank you. And then I'll follow up with one more question after a reminder. Thank you. God, I see. Oh, thanks, Gabby. One more question after just a reminder to everyone. Additional questions for Scott, please post in the chat. My second question actually is in your list of best practice roles for integrating HVAC and lighting controls. Um, you mentioned at the end of the process a commissioning technician. And so I'm curious, that commissioning technician, what type of training would they need? Would that be someone that might come out of a building sciences program at a technical college, for example? Or who would you expect that person to be? What kind of training might they have?
Yeah, so there's commissioning agents is a broad job that doesn't just focus on advanced lighting controls. They are a pretty important part of any major retrofit or new construction project. They're typically a third party that's not employed by the contractors or design teams, and their role is to make sure that everything in a building was installed per the design per the design intent. Um, and so, yeah, they could certainly come out of a technical college. They could get training. They could come from from the design field, but they tend to be people that are more hands-on and want to get into real buildings and make sure they're working well. A part of their scope is looking at the control sequences, um, as I'm alluding to in this presentation. And so definitely someone with attention to detail is really important, because there's a lot of specific details and designs of these systems.
Yeah, yeah, great. Okay, so you do see them. You do expect those people would come from multiple roles. In your studies, did you find, is there also built in a recommendation for some follow-up analysis? In other words, someone will come through and do commissioning to check to make sure that everything is being implemented and following schedules properly. But then do buildings drift over time? I mean, you mentioned occupant feedback, for example, and initial task tuning setup. Any specific protocols for, a timeline follow-up in a year or 6 months or something like that to assess if everything is still functioning as planned?
Yeah, so that's definitely best practice. It's much less common than the commissioning that occurs right at the end of the retrofit or new construction. There's been a little bit of progress made in that regard with respect to the systems themselves having the capability to report
Oh,
if they if their performance is degrading over time, both in terms of dashboards with power and energy summarized, as well as alerts around whether or not controls have been overridden, for instance, manually. So that is improving the situation, which you're alluding to a problem, which is that most systems in most buildings performance degrades over time. Not just because the gears get worn out, but because the controls get overridden. The space type changes, things just change and things tend to get worse performance wise. So I would say there's a little bit of room for improvement with automation. Doing it manually with a person's time is probably going to be too expensive for the value you gain. So I'd look to automating that process as much as possible to help make it economical.
that's interesting to point out that trade-off. It seems to me to be akin to what you were saying before about doing some task tuning by coming into a building and making measurements, as opposed to using lighting recommendations and laying everything out in a plan document rather than actually making measurements in the space. Um,
It is, yeah, there's always this trade-off between if you get a human in the loop, you're probably going to do better, but it's going to cost a lot and you probably won't. And for most people, that means you're not going to do it at all. So, so yeah, is there a balance there? Some organizations, a small niche, will be willing to pay for the extra benefits that the person can provide. Um, but if you can do it quicker and less expensive, but not get quite as much savings, that's going to be more applicable to a broader set of folks.
sure. Thank you. We've got a question in the chat. This is from Ed Franklin. Ed's wondering, when examining older buildings, especially those with classrooms and lab space like you might find at a technical college, is there a tipping point where the investment just isn't economical anymore?
A tipping point with respect to the age of the building, or
I think so. Ed, if you're still here, do you want to follow
Yeah,
up on that?
yeah, absolutely. Scott, thank you very much. What I'm looking at, yeah, if you have an older building and you're thinking about doing a retrofit um, to upgrade and put this technology in there, is there a point where you're saying, no, it may not be economically worth it to all the changes that have to occur in the infrastructure?
yeah, the way I've been thinking about it is that if you're retrofitting the lighting fixtures for some other reason, whether they're end of life or there's a change of use of the facility, then it's most economical to add advanced lighting controls into that retrofit project than to try to add it later after a retrofit of the lighting has already occurred. Um, there's an edge case there in which you've purchased a new lighting control system that's capable of all these things, but for some reason you didn't implement them. If that's the case, you should definitely go implement them because that's a very low cost set of controls to adjust. But it's not usual that people will retrofit all the lighting in the space and purchase the controls but not use them. More typically, it's you're putting LEDs in a space and you don't purchase the controls. It's like just a one-for-one fixture replacement in which you're putting either LED fixtures or TLEDs in. You're just putting
Right.
new LED bulbs in. In that scenario, you're going to get a significant amount of savings over the existing lighting system, maybe 50%, at a pretty good simple payback. If you want to go deeper, then you have to pay more to get the advanced lighting controls. you get another 20% savings, but your simple payback jumps from 1 to 2 years to 6, 7, 8 years. That's how I tend to think about it.
Great. Do you know of any grants that are out there that would help, facilities do that?
Yeah. Most utilities, most electric utilities will have some amount of incentives or rebates available
Okay.
for certainly just the LED only retrofit, and then they'll be able to provide additional incentives for going to advanced lighting controls.
Great. Thank you.
For sure.
This has been a great presentation, everyone. Scott, we're very grateful for all of your work in this area, for providing a lot of free resources, and also for coming to give us an overview of it today. I don't see any further questions in the chat right now, but I'll just end with a reminder. We do have those upcoming events that we mentioned before. And so Gabby's got that slide that you can see right there. Please check createenergy.org for updates and watch your email from other updates from Create. I think that is going to conclude our work today. Scott, thank you very much. Great to see you.
Yeah, great to see you all too. And if you have any other questions, feel free to follow up. And certainly, Gabby, you're welcome to share these slides with everybody if they're interested
Thank you,
that.
everybody.
Thank you.
Goodbye.
Yeah.
Thanks, Scott.
Great to see everyone. See you
Thank
soon.
you.
Thanks, Scott. Thank you, Gabby. That worked really well.